welcome. Last time I was still not knowing what the upper bound is for the arboricity of higher dimensional manifolds. That has collapsed, and it's actually very easy. The arboricity can be arbitrarily large for manifolds of dimension 3 or higher. Especially for 4 manifolds, I will say something about 4 manifolds because there is almost nothing to say here. What happens is you can, just with one picture, you can show this. So if you have an edge, then for any manifold you can do an edge refinement. It's not barycentric refinement, it's a local refinement. You add a new vertex and then you take the SA intersected with SB. You connect this new vertex with any vertex in the intersection of the two spheres, which is a sphere, right? So this is a codimension 2 sphere. So in dimension 2, this is a codimension 2 sphere, which it means it's a 0-dimensional sphere, which means that that sphere here, so that sphere in this case is just consists of 2 points. A 0-dimensional sphere has cardinality, vertex cardinality 2, nothing more. With a picture, you add a new vertex and then you connect everything. You connect everything to that. So in this case, you add a new vertex and you make this edge refinement. You add a new vertex here of vertex degree 4. That's very interesting, but you can do that again and again and again. But what happens every time you do that, you add one new vertex and you add 3 new edges. You cannot make this arbitrarily large, while here in this SA intersected with SB is at least 1-dimensional sphere. So what happens is the cardinality of a sphere can be arbitrarily large. So what you do first, you make edge refinements to make these unit spheres larger and larger. You make, for example, an edge refinement here. And so the first step, you want to reach some cardinality. You make here a refinement such that some sphere intersection has, sufficiently large cardinality, and then you add a new vertex, which increases suddenly the arboricity or this Nash-Williams ratio as much as you want. So this is a kind of funny difference between dimension 2 and dimension 3. Similar in probability theory, you have recurrence in 2 dimensions and you have, transient behavior for almost all random walks in 3 dimensions and higher, according to a theorem of Poincare. So we have kind of a similar threshold here. Dimension 2, the arboricity is 3 or 4, or in dimension 3 or higher, the arboricity can be arbitrarily large. Another thing which is the lower bound, if you just want to look what happens with the lower bound. To see the lower bound, one just uses the Euler handshake formula. So Euler handshake tells you that the 2e is the sum of the vertex degree. The vertex degree in dimension d is at least 2d. So this is bigger or equal to 2d. So we have a 2e over b is bigger or equal to 2. So that 2d. And then what we have is, then this means that e over v is bigger or equal to d. That already determines that the arboricity is bigger or equal to d plus 1. But still, kind of now the interesting question is, what is the lower bound really? Say for a torus, what is the lower bound for an arbitrary D manifold? So does it depend on the topological type? So there are still questions which are open, but I'm very happy here kind of with this kind of, low-hanging fruits. So here's something just about some reminders about 4 manifolds. I worked with this, almost 10 years ago, starting with 2011 or so, about the curvature of lower dimensional manifolds, and then saw the pattern. So this is a differential geometry of manifolds. So a manifold is kind of just very conveniently defined as a graph where the unit spheres are d-1 spheres. So for 4 manifold, every unit sphere is a 3 sphere. And so the Euler characteristic, that's already Schläfli has looked in higher dimensions at the Euler characteristic. And then we have this curvature, which I looked at more than 10 years ago. And so there's the Gauss-Bonnet theorem that works for any graph. It doesn't have to be a manifold. You have this curvature continues, of course, also in higher dimensions. You can do that, and so there's the Gauss-Bonnet. It's actually Gauss-Bonnet churn because of this index story. I will maybe say something about this index story, but it's very nice. I was very proud here about this, discovered this Dehn-Sommerville, and the reason why I was interested in that, because this explains immediately using just some system of equations. If you take these equations and you take the unit spheres in 5 dimensions and you look at the curvature in 5 dimensions, it's 0. I could not prove that in 2011 yet, and so index expectation and also Dehn-Sommerville are 2 tools to verify that, and they are all related also with barycentric refinement. So you can read off from a matrix, you can read off these numbers. I was actually very pleased about this because Dehn-Sommerville is something a little bit mysterious, right? Dehn and Sommerville have discovered that early, and then for decades nobody was really looking at it, and then Clay was looking at it again and kind of popularized it, and then it is now in combinatorial topology. It is usually used. It's umbral type mathematics with lots of binomial coefficients. I got rid of the binomial coefficients and I just looked at looked at functions, the Dehn-Sommerville functions, and so this is, and then Gauss-Bonnet, look at Gauss-Bonnet, and then you can see things like that. So this is true for any 4 manifold. You can look at the number of edges, number of chambers, number of faces, triangles, number of hyperchambers, and this always satisfies this relation. I just wrote you down a couple of examples of manifolds. I wish I had a more kind of, you know, a bit better library of 4 manifolds. There's a huge amount of 4 manifolds you can build, and so it would be kind of interesting to experiment. Lower bounds of arboricity would be kind of something interesting to investigate. So that's this Gauss-Bonnet, that's Dehn-Sommerville. This is related because Dehn-Sommerville allows you to prove that in odd dimensions the curvature is always 0. But here we are in even dimensions, so the curvature is not 0 in general, and so there are some conditions under which you have those Euler characteristic positive. There's a famous Hopf conjecture which you know, asks whether a positive sectional curvature implies positive Euler characteristic, which is solved in dimension 4 and 6, but not higher. And here in this kind of case, this manifold as 2 cross S2 is also interesting. Traditional differential geometry, because one doesn't know whether there is a positive curvature metric on that manifold. So it's lots of interesting question. Of course, there's also the Poincare conjecture, the smooth Poincare conjecture, you know, which asks whether if you have a manifold which is not only simply connected but also the homotopy of the second homotopy group is trivial, whether this is then smooth in the smooth category, whether this is equivalent to a sphere, diffeomorphic to a sphere, which is an open problem. There are lots of interesting, there's a lot of interesting mathematics for 4 manifolds. I love that, and I wrote this down once in a 2-page paper, submitted it to the archive, and then these damn bots were just labeling it as spam because it was just 2 pages and had not the format for usual thing. So AI is not really the hit. So very working very hard to get this on 2 pages so that it could be tweeted. So these are tweeted ones, and I'm very proud about kind of seeing this relation. Even so, it's a classical topic, you know, kind of rediscover a classical topic, which is usually not stated like that. Also kind of interesting is, in this context, is curvature you can see as an expectation of indices. So indices, these are Poincare Hopf indices, which are, you know, I like to think about them as divisors because they're integer valued. So you have then finitely many. Of course, this is all finite, but also in the continuum you have finitely many points on which the indices, critical points on which the indices are defined. And then what you can see also in the continuum, you can see curvature as an expectation of indices. It's Fubini, because what happens is you have the theorem, the Poincare Hopf theorem here, and you take the expectation. This is an integral, right? So and then a sum, and you take the now you take the expectation of that. Of course, the expectation of the Euler characteristic is Euler characteristic. So from Poincare Hopf, taking expectation, you get immediately the Gauss-Bonnet theorem, and you can see then understand Gauss-Bonnet or the curvature also better, because what happens is this index here, if you take the index of G and minus G in a manifold case, has kind of a nice, there's a nice formula using a codimension 2 manifold, which is always a manifold, which is very, very nice, which follows from Sard's theorem. Very happy about this Sard theorem in the discrete. Completely surprising that this is always a d-1 manifold. If you have a hypersurface, it's always a d-1 manifold. There's no singularity possible if the value of the function doesn't take a value of one of the vertices. In the continuum, you just know only for almost all values. So I call it Sard's theorem. And so that's very nice. And you can iterate that. So in this case, actually, this is a submanifold of the unit sphere, which is a codimension 2 manifold. If the manifold is odd, then we have not the 1 here, but then what happens is we have also a codimension 2 manifold, and then you see that there is the expectation of Euler characteristic of odd-dimensional manifolds, which is 0. So you see also without this Dehn-Sommerville, you can see that the curvature of an odd-dimensional manifold is always constant 0, which is very nice. So this is a nice story. I love this also because what it shows is the Euler characteristic is an expectation of Euler characteristic of two-dimensional manifolds, which you can attach at every point of space. So at every point of space you have a 2 manifold, and this can have some genus, can have, you know, higher genus. Actually, if it is a sphere, then it's 0. So it can also consist of 2 spheres, so it can become negative. So 2 spheres or 3 spheres or 4 different spheres. It is just a two-dimensional manifold, not necessarily connected. It's very cool, and but it's just a little bit of integral geometry here, which links differential geometry with differential topology. So differential topology deals with kind of functions G. But it's very cool. So there's some really nice elementary differential geometry. You have an explicit curvature which you can write down in every concrete manifold, 4 manifold. You can write down this curvature explicitly by counting stuff, and then you have this curvature which adds up to Gauss-Bonnet. You can also compute infinitely many steps. You can compute these Betti numbers, which are kind of cool, and so that's very interesting. In 4 manifold case, the kernel of L2 is very important, because these produces an intersection forms. In 4 dimensions you can take 2 form cup product with another 2 form, then you get the volume form, and you can see how many times this is bigger than the usual volume form. So you have interesting numbers. 4-dimensional manifolds are special and nice. So let me wrap up this for now.